Welcome back, my statics friends. In this video, we're going to spend some time talking about a special type of moment known as a couple. Now, we defined this previously in a couple of videos back, but I'm going to kind of show you the two-dimensional form and the calculation for it, and then I'm going to show you how we can apply this to a vector form as we start to move into how to do vector operations. Okay, it's kind of an interesting but can be confusing at times. It's an interesting topic. So without further ado, let's get started. All right, so if you recall from our introduction to moments video a little while ago, we defined a couple as being a pair of parallel forces acting in opposite directions but causing a rotation. Okay, and we calculated, so the version I showed you early on was basically a simple two-dimensional sketch in which I had a force to the right and a force to the left, and they were separated by a distance. Now they're the same magnitude f, one is positive, one is negative, that's a couple. And we said that we could calculate that m was equal to f times d. For that, again, d is perpendicular. Now when forces are horizontal or forces are vertical, getting d is no problem. But what happens if these forces are parallel but they're not in the same plane, or they're at some angle to each other, to their coordinate system? It becomes a little bit more complex. So I want to show you where the formulation comes from for the m vector. Okay, and so what we're going to do is we're going to choose an arbitrary point in space. Here are my forces f. Here's a positive f here, a negative f here. Okay, and they're separated by some position vector r. Now again, when we start playing with vectors, this requirement of perpendicularness does not matter anymore. It can be anywhere. As long as I'm on the line of this guy and the line of that guy, the r between those 2 points, it can be any two. So I'm going to arbitrarily call those as, point B on this force and point A on this. I'm going to define r from A to B. So if we want to put some subscripts on that, that's r from A to B. Okay, now it doesn't matter which way I go either. I'll still get the same effect. I could do r from B to A and cross that into the negative f, and we're good to go. So what we're going to do is we're going to look at, I'm going to choose an arbitrary point O down here out in space somewhere. Okay, and we're going to say that I can define a vector from O to B. That's how I get the position of B. Remember, that's how we kind of did it in calculus to get the coordinates or a position vector of B. And then I can do R from O to A, which is what I'm calling RA. Okay, now if I look at that, then the moment on this, if you look, remember for the m vector, we're always looking at r vectors crossed into f vectors. Okay, and so if I write the equation here, this moment vector then is going to be RA, which is the first one, okay, crossed into the force that's on that line. That's the minus f. So RA crossed into a minus f is this one. And then plus RB crossed into a positive f. Now it's a plus here because we're doing vectors. This is a vector and this is a vector, and all we're doing is we're finding the resultant of these two guys added together to get the total for our moment of our couple. Okay, so if I do the math and I kind of rearrange this, I get what is, an RB minus RA vector crossed into f. I'm just doing a little bit of kind of using one of those identities and backing out the pieces of it. Okay, where we can do the distributive property, if you will, on this. And so this is the calculation that we're doing on this. All right, now if we look at this and kind of recognize this, there's something interesting that we can do. Let me flip over to our next page. All right, then we can say, all right, well, let's just take a look at what's happening with these position vectors. So here was my point O. Oh, whoops, point O. This was my point B. And this was my point A. Okay, and we know that this is R from A to B. Okay, now if you look at what's happening on this, if I look at the vectors in their arrow directions, we had RB we defined from here to here, put an arrowhead here, and RA was here with the arrow pointing at A. Okay, and then we defined RAB as being the distance between the two vectors, starting at A, ending at B. So the arrowhead was pushing at B. Now if you look, what you've got is now a system of vectors in which there's a vector here and a vector here, head to tail construction, okay, which means then that this guy is the resultant of these two guys. Okay, now if you remember, so if this is RA, if we write our vector relationships of this, RA plus RAB is equal to RB. That was our vector addition for these position vectors. Okay, which means then that if I rearrange this a little bit, that RAB vector is going to be equal to RB minus RA on there. Okay, well, if you look back at our formula that we had on the previous page, pull this down a little bit, that's this guy. All right, so if that's the case, then this is going to become R from A to B crossed into F, crossed into the positive F, because this guy is acting on the positive F that's acting at B. All right, and so we can get back to our basic formula for the moment vector. Okay, so really, even though we did this really convoluted system of choosing any point in space, I didn't put any restrictions, no perpendicularness. I don't care where the point. It could be over at the top, it could be up at the bottom, whatever the case may be. It's still an R cross F. And for us, then, the moment vector on this would be our F at B crossed into R from A to B, and that would give us a moment, of what this couple is doing. Okay, and one way that you can kind of follow through on this is if you watch the subscripts and you put subscripts on everything, it's from A to B on the R. The second letter here has to match a letter here. This F has to be acting through B in order for this moment to work. Now, the moment itself can be anywhere. This is what we call a free vector. I can move it around. Okay, and so if we look at, whereas if I did the scalar method of this to be able to calculate it, the moment would be about an axis that's perpendicular to the plane containing these two forces. Okay, and then this would cause a moment to wrap around that way. I would be bounded by having to have this restriction of a perpendicular distance d there. Okay, so our moment is going to be equal to force times distance scalar, and so that's a magnitude of m is the magnitude of f dotted into d, and the requirement here is that d has to be perpendicular. Okay, so there's different ways to get there. The vector form by far is the easiest, right? Because here I have to have d perpendicular. Here I don't. I just need 2 points on the lines of the force. Okay, or line of action of the force, so we should say. All right, and so that's what we can do. Once you have these moment vectors figured out, I can always add them together. If I calculate a moment vector number 1 and a moment vector number 2, I can then add or subtract them accordingly, and that gets me a resultant moment. So that's the same rule that we had with forces. Remember, we said Fr was equal to F1 plus F2, so forth and so on. It's the same game because this is now a vector, and it's, we don't care whether it's a moment vector or a force vector. It's a vector, and so I can find resultants and components and so forth and so on. So that's one thing that we can kind of look at. All right, so let's try a couple of scalars just to get kind of a practice on this. Okay, then I have a system in which I'm looking for the equivalent force couple at A and B, and then an equivalent force couple for D and E, if you will. Okay, so all I'm going to do is it's kind of like a bracket here. Maybe it's a beam with a couple of angles holding it to the wall. Okay, the moment that is caused on this by this couple, say I have a 400 Newton force acting here and a 400 Newton force to the left acting at the bottom, and they're separated by a distance of 0.2 meters. Okay, well, that's the same thing then as this beam, which is now 400 newtons times 0.2 or 80 newton meters with a moment going this way. Now, again, that's what we're looking at the direction. This couple is causing a clockwise rotation about an axis here, somewhere in the middle. Okay, and so then this guy is causing a clockwise, his resultant is a clockwise. So this picture is the same as this picture. So that's the first simplification. Anytime you see a couple, replace it with this guy, and we can do a kind of a 2-for-1 kind of thing. All right, so now if I want to find the couple that is induced at the A and the B on this thing of this 80 Newton meter force, well, now I have what would be a force in this bolt here, assuming that it's negative, and a force in this direction is positive. This will cause the same direction on this. Okay, and so the equivalent forces at this location, which I guess technically they're not the forces in the bolts, but the equivalent forces acting at those 2 points, I could say, well, that's 80 Newton meters multiplied by F now times a distance between here and here of 0.25 meters. Okay, and so the force that's produced here at these locations then is going to be, so I have 80 Newton meters is the moment, F times 0.25 meters is the perpendicular distance between these two F's. This F would be 320 newtons. Okay, so we went from a 400 Newton force here that was fairly close together. I can reduce those forces by spreading out the location of the bolts. And that's one of the tricks to connections, is to be able to get very wide bases on connections, that I can take applied forces and reduce them at their connection location. All right, so that's that one. Now, we could also produce a moment, say at D and E, which are these 2 points here that are located at 0.1 meters. Okay, so the same 80 Newton meter force could be replicated by a couple on these 2 points, in which P is up on the left and down on the right. So these two guys relative to this point are going to cause it to go in the clockwise direction, which matches what I have. Okay, and so I could say, well, what does the force have to be there if we have 0.1 newtons in the middle? And so it's 80 Newton meters is going to be equal to P times 0.1 meters. Okay, well, P is now 800 newtons. Okay, so it actually goes up because I've squeezed those things down. And I can put these couples anywhere that I want, and I can move this force around, or sorry, move the moment around, because the moment is a free vector. And that's the definition of a free vector. It can be applied anywhere. Even though I started out saying, oh, we're going to apply it here, okay, it can actually be pushed anywhere, and I can find out the equivalent effect at any other location, kind of doing some games like that. And we'll do a lot more with this. This is kind of an equivalence problem as we start to kind of look there. All right. Okay, so I think that's all we have. Oh, no, I apologize. Got one more. So what do you do on this one? It's still a cantilever beam. And so now I have a force acting at A, okay, which is located at 2 feet from the wall, and then a force acting at B, which is located at 5 feet in the wall, and then it's 1 foot between A and B vertically. Okay, and if I look, I now have forces that are inclined this way and this way. Now they're parallel. They're both at 3, 4, 5 triangles, so that's the line. Now, what we mean by 3, 4, 5, this is a proportions method. That means that for every 4 units I go over, I go up 3. Okay, so it's kind of a way of getting this. So if you wanted to get the angle, you could calculate that angle right there. Okay, or we can take advantage of this, and we'll do some more with proportions here in a little bit. That 3, 4 on a parallelogram, because that's 90 degrees, vertical, horizontal. Okay, gives me a 5 on this dimension. Well, if we kind of blow this up, we've got the cosine of theta, where theta is that angle. So let's just draw it this way. Here's theta. Cosine of theta, then, according to this, would be 4/5, and the sine of theta then would be equal to the opposite 3 over 5 is one way that I can write this. Okay, and there's some advantages to why we would do it with proportions. One being that whenever you take a trig calculation of any angle, you always get an irrational number, almost always. Whereas writing it this way, I now get that the cosine of the angle is 0.8. Okay, so now what we want to do is we want to find the equivalent couple that's produced on this system. What's the net moment effect happening as a result of this? Well, one way that I would tackle this, and this is kind of a trick to handling angled forces, is I break it up into components. Okay, and so I could say, well, let's take an F and a P at this location. So P is the horizontal, F is the vertical. So this force, in order to break it down, since my force is acting this way on that, then the P has to be to the left and F has to be down in order to produce that resultant. Okay, and again, we're looking at this point here. Okay, so then how do I calculate this? Well, this is the horizontal component of this guy. And so we know that to calculate P, I take basically the cosine of theta of my angle theta that we had up here, and I multiply it by the magnitude of the force, which is 150 pounds. Okay, now you may see a character that looks a little odd. Okay, I've written that symbol, the number sign, or I guess nowadays it's a hashtag, right? This is an abbreviation for pounds that you'll see in a lot of older engineering calculations, and this is something I do out of habit. So if you see me write that, that's what I'm talking about. So I'm doing the cosine of theta, or 4/5, multiplied by 150 pounds tells me that the horizontal P guy is going to be 120 pounds. Now, I didn't put a direction on this because this one is to the left and that one is to the right. Okay, so we'll worry about signs here in a little bit, and that's one of the problems with doing scalar magnitudes type calculations. Okay, the F, similarly then, would be the sine of the angle, because I now want the vertical piece and we're defining theta there. Okay, so the sine of the angle, which we said was 3/5, remember? Sine of theta, 3/5 right there. Okay, multiplied by 150, it's going to tell me that or is that the F force is 90 pounds, and it happens to be that it's down here and up here. Okay, now if you look at what we've done, we've resolved this one couple of two forces at an angle into now what would be two couples of forces. One set is horizontal and the other set is vertical. So if we remember what we do with our moments, the moment arm for the P forces is the perpendicular distance, 1 foot. The moment arm for the F distance is the perpendicular distance, or 3 feet. So the moment equivalent of both of those guys acting together is we do F times 3. Now if you look at the way this is rotating, this is going counterclockwise because F is down here and up here, so it's wanting to spin this way. Counterclockwise, we said that was positive there. And then P is going to be to the left here and to the right there relative to a point in between. This guy is also going counterclockwise, so that's why he's a positive. Okay, and his distance now is 1 foot, so it's F times 3 plus P times 1. I can plug in the numbers. 90 times 3 plus 120 times 1. It's going to give you a total couple effect of this one of 390 pound-feet acting positively or in the counterclockwise direction. So that's what we can do with these couples. You can break them apart, recombine them, you can do all sorts of things. Okay, but now you have the ability to handle forces in any two directions for scalars. Okay, so that's one of the tricks that we do. If a force is at an angle on a scalar product, often I break it into horizontal and vertical components because typically on an engineering drawing you know horizontal and vertical dimensions. Not always, but most of the time you do. Okay, and so that's one way that I can use this to actually resolve this couple problem. So the equivalent couple of these 250-pound forces is 390. Now I could back out and say, well, what's the perpendicular distance between those lines? If I took 390 and divided by 150, I could get that. It'd be somewhere around, a little less than 3, 2.7, 2.8 would be the perpendicular distance between those two lines and spaces. So anyway, that's what we're doing with our force couples. So I hope that's made sense to you. As always, leave us some feedback down below, and I will get back with you, answer any questions that you might have, and then, of course, be sure to like and subscribe to the video. So thanks, and we'll see you guys next time. Bye.